Welcome back to our series on multivariable calculus. In this episode, we're going to extend our application of line integration to the physics concept of work. To review, we looked at a line integral last time, which was an integral over some curve of some function in x and y, and then we wanted to multiply it actually by the curve length itself. And of course, that was the first derivative of the curve, that is the velocity of the curve, dt. And basically when we integrated along that, it was going to find the arc length for us. And then f of xy would then take the value that we were at on the arc and extend it upward in order to perform the line integral, to basically find a wall-shaped figure whose bottom was defined by the length of the curve and whose top was defined by some capping function z as a function of x. Well, we didn't really have an application for it. That is, this was just a purely theoretical construct. So let's take a look at it in a couple of different parameters, and then let's talk about an application, that is the idea of work from physics. First, to rewrite this integral, we could rewrite this as basically just a function of f, again, of x and y, ds, where ds just generally represents the length of the curve. In other words, it would be the differential along that length. In our particular case, because we were usually provided with the length of the curve either by its endpoints or by an r function that actually traced the curve, a parametric function, we express the arc length ds by actually integrating along dt using the first derivative of the arc itself, r. But it didn't have to be that way. That is, we could have expressed ds in a couple of other ways. And let's take a look at that by critically examining what r prime dt really is. And then let's look at some expansive ways of examining what this f function actually represents. Because if we look at it this way, we'll be able to see its application to force and subsequently to work. First of all, ds. We've looked at ds as being equal to r prime dt. But let's open up r prime itself. Remember, that in and of itself is a time derivative because r tends to be a parameterized function of x, y, and we could even expand this out to z. So this is dr dt times dt. And that means it's really a differential itself. ds is just dr. Now, dr, how would we obtain dr if we really had a definition of it in terms of a parameterized function in multiple variables? Well, keep in mind that if r's definition, r of t, is really something like x of t, y of t, and let's expand it out, z of t, so that we've got the three components that r could be. Well, dr then would be, and again, this would still be a vector function because it would still be broken into three. That would be dx dt, dy dt, and then dz dt as its three components. And then I would just multiply that by the dt differential. And you'll notice now that if I multiply this inside, this is a scalar quantity times the vector dx dt, dy dt, dz dt. What it's going to produce is just this dx, dy, and dz differentials. And so that's how we could go about doing it. That is, dx, dy, and dz is just a different vector path of integration. We'll see more on this in a little bit, but basically if I integrated along dr, I have two choices. I can either integrate along dr by utilizing these as its components and integrating with respect to t, or instead I can use dr as these components and then integrate with respect to space. That is, my individual integrals for x, y, and z would have to be the change in position as their limits of integration, whereas expressed in terms of dt, it would be the change in terms of time, and I would need the initial and final time. Very similar to how we dealt with integration of vector curves earlier in the year. We could integrate them either over space or time, and the same will occur here. Well, let's take a look at our first application. That's the idea of work. Of course, the physics definition of work is it's the integral of the force function dotted with the change in path. And we'll use the general ds for that as well. The reason it has to be a dot product is I'm not interested in the actual length of the curve ds with f projected on top of it. F itself is a vector curve, and I'm interested in the degree to which they point in the same direction. And that's where the dot product comes in. Fortunately, though, the dot product is a scalar product, and so I don't have to retain any vector nature after I perform this integral. You'll see that what we've already done with line integration already gives us a path, no pun intended, for how to solve this particular integral. We actually have some choices. Because f itself is going to be a vector function, it's the vector force, it's going to have components. And I'll call those f, g, and h. So those represent the three spatial portions of the vector force. Now ds is really the same as it is over here, just in terms of a general path. Now it's a vector path, that is, it has a preferential direction, whereas when we were just referring to ds here, it was just a curve length, but it didn't matter whether we started at any particular point or headed in any particular direction. Well, the same will hold true in terms of how we evaluate ds. So we can call ds just plain dr. We can see that we've made that comparison right here. But we know that opening up dr gives us two possibilities. Dr is either the individual derivatives of dx dt, dy dt, and dz dt, and then integrated with respect to dt. So let's take a look at what that one would look like. So I can say it's the integral over the curve for work of f, which is f, g, and h as a vector, dotted with, again, if I express dr in terms of dt, it's going to be dx dt, dy dt, and dz dt expressed as a vector, and then that dot product will be integrated with respect to t, which means in choosing the curve, all I have to do is figure out in the path that I'm integrating over, what's the initial time and final time. So this would be a time integral of the dot product between spatial functions, but these spatial functions would be defined in terms of time. Now, in order to perform this, of course, this is going to be f in terms of x, y, or z. The individual components of f aren't limited to f being just its x component. Its x component can be in terms of y or z. So what I would need to do is use the parameter for r. Remember, r of t is still going to give me parameters for what the x is as a function of t, what y is as a function of t, and what z is as a function of t. And I can use r to make equivalencies between x, y, and z so that I can make f entirely in terms of t itself. Same with g, same with h, so that these would all be functions of t. I'm multiplying by derivatives that are functions of t, and I'm taking the integral with respect to t. So this is one option for calculating the integral. It requires one set of limits of integration, and it requires that f, g, and h, if they were provided in terms of x, y, and z, need to all be parameterized and converted to t. So this is one option, and it's certainly viable. Once I evaluate this dot product, of course, it'll be f times this, g times this, and h times this. It will give me sort of three individual integrands that are summed together, but integrated individually. And when I'm done, I'll get the scalar, which represents the work done. Here's the second option. The second option is to do it spatially. That is, I can consider multiplying dt inside of here and converting r into this version of itself, a spatial integral. Now, of course, that means I'm going to need three integrals to do it. I'll need the integral over the curve of f just expressed as a function of x. And then that will be times dx. And then I'll add to that, again, a new integral over a new curve expressed in terms of dy. And this will be g expressed solely as a function of y, dy. And then the final one will be c, again, a curve defined by z. and this will be h exclusively as a function of z dz. The difference is the above integral will be a time integral expressing the function f entirely parameterized so that it's all t's. In the bottom one, I'll still have to do some converting because if f is in reality a function of x, y, and z, I'll have to do some substituting for that y and z because I can't integrate a function of y and z in terms of dx. I can only integrate a function of x. This is not a partial integral, and this does not represent a partial derivative. It's whole and entire, and so I'll have to do the substituting. So it kind of gives you choices when provided with the need to calculate work. You can express this dot product either temporally or positionally. And of course, you could try one of them both ways just to convince yourself that the answer for the work done is the same in both cases. You'll also notice something subtle. If you are a current physics student, you know that, of course, work is always the negative of the integral of the dot product of the force along its path. And in this case, we're just really looking at the magnitude of work. So keep that in mind. The rules haven't changed. To really be calculating physics work, this should be the negative. In other words, all of our answers should be the negative of what we're actually getting. And again, that negative is due to the fact that when the force and the displacement lie in the same direction, you can expect an increase in internal energy for the system. And that means work is done on the system, and that means the work is considered negative. When the work is done by the system, that means you'll get a difference between the direction of F and ds. That is, they will point in opposite directions because you'll be having to add work to the system as opposed to having the system work for you. So that's what the negative is for. It's whether this dot product yields an angle between F and ds of less than 90 or greater than 90. And that's really what controls whether the sign returns positive work or negative work. As I said, that's more of a physics concept than a math concept, which is why we've chosen to simplify it in its math application and simply look at the magnitude of the work done. Okay, so in future problems, you basically have a choice. Based on the scenario, you can choose to do it temporally or positionally, and either will produce the same exact result.